Here we're going to complete our look at exponential modelling by looking at something called a logistic model, which I think is a much more accurate way of looking at something like the spread of a virus. And it's not something you've seen very much in the media recently, but hopefully you will agree that this is a much more mathematically and realistically accurate representation of what will happen over the course of time with something like a virus. So what you've seen so far probably are models that are essentially just exponential. So they start off down here and then they very quickly rise up and get much larger. Now that is an accurate model for the early stages of the growth of a virus, but of course, even if a virus is extremely infectious, there is an upper limit to how many people it can infect, because there is an upper limit to how many people there are in the world. So over time, this growth cannot continue at this rate. It's just not possible. It has to level out eventually. So a more realistic picture would be a beginning that was steep like an exponential, but eventually ending up at a top level with a curve like that. And that's what a logistic model does. So a logistic model is something that has exponential aspects to it, but has an upper and also actually a lower limit to it. The data in the example here is the progression of men's high jump world records. So it grew very quickly in the middle, but obviously eventually reached an upper limit, because there is a point where people just cannot jump any higher. Now the equation for logistic modeling is this. Looks a little bit complicated to begin with, but it's just a rearrangement of what is essentially an exponential model here. So there's the exponential part there, and there's a few other parameters which have been inputted to give the graph its very characteristic shape. So we need to look at one in particular, which is the L up here. Now the L is what we call the carrying capacity. But that just means the upper limit, basically. And whatever L is, it will produce a horizontal asymptote at that value for Y. So if we go back to our graph here, let's say that the graph I drew here, let's say the value up here on the Y-axis is 100. That means that our equation would have L equals 100. Now there's a couple of other parameters as well that we need to think about. There's the K here, that's a very important one, that affects the shape of the graph, and also this C will affect the shape of the graph. I want you to explore that a little bit yourself by, on the second page of the exercises, are these four functions here. I want you to plot these in Desmos, and they change a little bit each time. That's the best way for you to see how the changes in these parameters actually have an effect on the graph. So do that, and you'll then see that there's a couple of questions using the model, and we're going to go through a real world example with some of the things that are going on in the world right now, and see if we can produce a logistic model like this to model the situation with the virus. Now here's how you go about doing this. And by the way, question 3 on the exercise is a very similar question to this, so you can practice doing it with the data in that question. So the carrying capacity, L, is the upper limit of the function. It's how many people could be infected. So if we were making it for our situation that we're in, we would say that for this country, L is going to be about 70 million. Because that's the population of the whole country. That's a very rough estimate here. Obviously, if you were doing this properly as a proper scientist, you would use experimental data to make this as accurate as possible. I'm just going to make some numbers up, but you could get these numbers from data sources if you wanted to. So that's the upper limit of how many people can be infected. So I'm going to put L as 70 million. So something else we might be told is how many people are infected initially. Of course, if the answer to that is 0, then there's going to be no epidemic because no one's infected to begin with. But of course, there will be some people. So we will say that when x is 0, the function itself produces an output of, let's say, 100. So there's 100 people initially infected in the population. The x being 0 is important, that's time. Almost all of these questions, almost all modelling begins with some initial conditions. Initial conditions are very important. And that's when time, and in this case, x's time, is 0. That's extremely important because if you go back to the model here, if you replace the x with a 0, this whole thing becomes a power of 0. Anything with a power of 0 is 1, so that effectively disappears. It makes it much easier to work out other parameters in this problem. So what we're going to do is put in what we've got. So we know that the L is going to be 70 million. If I'm saying x is 0, then I can say 1 plus c on the bottom. Yes, really, we've got this e minus k times 0, but that is just going to be 1. So when I go to solve this, I'm not even going to bother with that. This whole thing, when x is 0, is meant to be 100. So I've got an equation here that I can set up and solve, and I'm going to do that using the GDC. So I go into the equation solver, and I just type in exactly what I've got. So it's going to be 100 equals, so I've got the fraction here, that's going to be 70, 70 million, 1 plus, and I'm just going to go with 1 plus x there, because the thing I'm trying to find has to be the x on the calculator, and it's c in the actual function, but we have to put it in as x here. So if we go to solve that, it tells us that x is 6999999. Okay, so that looks like it's 699,000 there. So that's our c. So I'll make a note of that. C equals 6999999. Okay, so that's going to be the c we use in the model from this point onwards. We're trying to work out also the value of k here though. So we need some more information in order to do that. So that's what you hear about when scientists are doing this kind of thing. They'll look for what happens as time goes on. So let's say maybe 1 week later, the number of infected people, let's be conservative, let's say it's just gone to 200. So it's doubled in 1 week, which is actually slower than the real thing, I think. That means that x would be 7, so 7 days, and then the output of the function would be 200. Well, the equation we're solving now is going to be equal to 200. It's still going to have the same carrying capacity of L on the top. On the bottom, we've got 1 plus, we know the C now is this number, that's the C, multiplied by E minus K, that's very important here, and this time it's multiplied by 7, because that's the X. So that's our equation to solve. We'll go on here and we'll do the same process, but with the new values. So let's go up to the equation there. I'll start from the left-hand side. So we've got 200 there, same number on the top, still 1 plus, but this X, we know that now because that was the number from before. So that's 699,999 multiplied by E. So go Shift and press that button there, and it's the power of, well, it's negative k, but we're trying to find the k, so we put in that as x, multiplied by 7, that should be good, and we'll go to solve, and it's given this as 0.99021, so let's round it off then. Let's say that k is equal to 0.099. Well, that's our model. So if we now put in all of those values we just found into the general model here and graph that, that will give us our logistic model for this particular situation. I recommend you go and do that on Desmos and see what it looks like. You'll see, and even with the relatively modest growth that we used here, it's an extremely steep curve, but that's just the nature of exponential growth. Okay, that's the last type of model we're looking at for now. So try the questions and let me know if there's anything unclear about that.